Right, good evening. Welcome to our presentation. So I'll be first giving an introduction of the entire paper, and I'll then read through the abstract, and then I'll explain the introduction, and I'll also give an introduction to a couple more theory, CMT, and then the rest will be taken on by my colleagues. So, right. So I'll just read through so our paper is Nonlinear Exceptional Point Lacing with ab initio Maxwell Bloch theory. The contributors to this paper are Aishman Sinha, myself, Adarsh Jadhav, Aditya Prakash, Atharva Arora, Devan Satra, and Jason Gomez. We'll be presenting a general analysis for finding and characterizing nonlinear exceptional point lasers above threshold using steady-state ab initio Maxwell-Bloch equations. For a system of coupled slabs, we show that a nonlinear EP is obtained for a given ratio between the external pumps in each resonator, and that it is associated with a kink in the output part and lasing frequency, which confirms coupled mode theory predictions. Through numerical linear stability analysis, we confirm that EP laser can be stable for a large enough inversion relaxation rate. And then we'll further show that the EP laser can be characterized by scattering a weak signal of the lasing cavity, so that the scattering frequency spectrum exhibits a quartic divergence, which will be the last segment. And then our approach can be applied to arbitrary scatterers with multi-level gain media. So going on to the introduction, first is an introduction to exceptional points in non-Hermitian systems. So exceptional points are special singularities of certain non-Hermitian systems where at least two eigenvalues and their eigenvectors coalesce and become degenerate. The reason they've attracted so much attention recently in photonics is because gain and loss can be used to tailor the non-hermeticity of the systems. And at these singularities, the relevant system operator becomes not diagonalizable, and therefore it leads to a response that is typically quite different from that of Hermitian systems. And they have mainly been studied in the context of linear photonic systems, and in laser theory, the lasing frequencies are the solution of a non-linear eigenvalue problem. And there has been significant interest in studying the analog of linear EPs for this physically important type of nonlinear systems. In this paper, we perform a comprehensive analysis for finding and characterizing EP lasers above threshold. We'll perform a comprehensive study of EP lasers above threshold using ab initio Maxwell-Bloch equations, which will then be complemented by a simple nonlinear couple mode theory or CMT model. Chronologically, the CMT will come before the ab initio Maxwell-Bloch equations. A nonlinear lasing EP can occur at a specific ratio of D2 by D1, I'll soon explain what D2 and D1 are, of the pump in each resonator, which depends on the loss rate and coupling strength. For such a laser, the EP corresponds to a transition between a PT broken phase and a PT symmetric phase. Also, this will be explained more in the future, but for now, PT means time parity or parity time. We shall also show that this EP laser can be stable enough for a large enough population inversion relaxation rate, and it is also characterized by a kink in the laser frequency and output part. The kink is owing to a discontinuity in the derivatives. Our analysis also further shows that the previously observed laser turn-off with increasing pump can be directly attributed to a virtual non-linear EP, which shall also be explained. And finally, as we noted, we demonstrate that the EP laser behavior can also be characterized by a scattering experiment, where the transmission frequency spectrum of a weak signal field scattered off the laser cavity exhibits a quartic divergence. So, moving on to the coupled mode theory, which I shall just derive by myself. Right. So if we have two coupled resonators with nonlinear gain saturation, the steady state solutions can be described by this equation. G1 minus kappa 1 G I G1 minus kappa 1 into psi 1 psi 2 is equals to delta psi 1 psi 2. Right. So here the delta is the relative frequency, G is the coupling rate, kappa is the loss rate, and then Gn, which is the gain rate, is actually dn divided by 1 plus psi whole square, where dn is the external pump and phi n is the field amplitude. Right. We shall also define xn is equals to gn minus kappa n for our solution. So the solutions of this problem usually satisfy 2 delta is equals to I into x1 plus x2 plus minus root over 4g square minus x1 minus x2 the whole square, where phi n, also phi n square will be equals to dn by kappa n plus xn minus 1, and phi n into I xn minus delta plus g phi m psi n is equals to 0 given m is not equals to n. All of these solutions will be in our presentation in our report as well, but I'm just working it out for everyone's benefit. So lasing solutions require a real delta, and two types of solutions are possible. First, x1 plus x2 is equals to 0 and x1 is less than or equals to g, and then we'll have real delta is equals to plus minus g square minus x1 square. And because of the threshold we have phi, so at threshold we have phi n is equals to 0, therefore d1 at the threshold plus d2 at the threshold will go to kappa 1 plus kappa 2, and these are called PT symmetric solutions. And to explain why they are called PT symmetric, it's because the loss and gain balance exists here between both the resonators, which is because x1 is equals to minus x2, which ties into our definition of x1 x2 here. The second type of solutions is for delta equals to 0, and as you might have guessed, it's called PT broken. It requires that x1 plus x1 into x2 plus g square should go to 0, and it's called PT broken because the gain and loss balance is broken between both the resonators. So gain loss balance broken, and so when this condition holds, there's another purely imaginary solution which is called delta equals to I x1 minus g square by x1, and the stability of the system, this will be more clear with the plot, but I'm just putting this out here mathematically for now, requires that the imaginary part of delta be less than or equals to 0, which means, so this condition implies x1 is less than or equals to g square by x1, which means x1 is less than minus g, or x1 lies between 0 and g. At threshold, so again at threshold, these modes at threshold, these modes shall satisfy this condition, d1 threshold minus kappa 1 into d2 threshold minus kappa 2 plus g square is equals to 0. The previous solutions are directly determined by the value of x1. So for each type of solutions, x1 can be found using d2 by kappa 2 plus x2 minus 1 is equals to phi 2 whole square, which is equals to delta I x1 by g phi 1 whole square, which is equals to x1 square plus delta square by g square into d1 by kappa 1 plus x1 minus 1. Right, so we'll call this equation 1. So for PT symmetric cases, equation 1 will simplify to x1 is equals to car2. So we're just putting in the condition that we stated for PT symmetric cases. So this simplifies to this, where phi 1 mod square is equals to phi 2 mod square, which is also equals to d1 plus d2 by kappa 1 plus kappa 2 minus 1, and delta shall be equals to plus minus g square minus kappa 2 d1 minus kappa 1 d2 by d1 plus d2 mod whole square. Right. However, for PT broken, the solution is significantly more complicated, but it still gives a direct value of d1, still gives a direct formula for d2 as a function of x1. It's very important to note here that for the previous solutions to be satisfied, so for all of the solutions to be above threshold, for solutions to be above threshold, we need that the mod of phi1 should be greater than 0, and therefore equivalently d1 by kappa 1 plus x1 should be greater than 1. And then an exceptional point is obtained at the boundary between the two types of solutions, so between PT symmetric and PT broken. And so this occurs when x1 is equals to minus x2 is equals to plus minus g, and delta is equals to 0. So if we plug these back in equation 1, we'll get the condition for an exceptional point, which is d2 kappa 2 minus plus g by kappa 1 plus minus g into d1. This is the condition for an EP. Right. So this requires that kappa 1 is greater than or equals to g, or kappa 2 is greater than or equals to g. And each of these two, so we have two corresponding exceptional points, and each of these are above threshold and lasing when we have, so the minimum value of d1, which can be kappa 1 plus minus g for lasing. So a way to obtain an exceptional point would be first increase d1 to a fixed larger value, which is greater than kappa 1 plus minus g here, and then we keep increasing d2 to get to an EP. So all of these things would make a lot more sense when shown with the plots, and they'll be a lot more intuitive to understand, but I have just worked out the math and given a bit of context so that things make more sense leading on to here. But from this point onwards, this will be taken care of by my colleague, and thank you very much for your attention.
Okay, so hi, I'm Aditya. I'll explain the power out P out and the related plots. So first let's see the derivation related to the output power of the laser. So the output power is given by kappa 1 phi psi 1 square plus kappa 2 psi 2 square, and if we do it for the PT symmetric mode, we will get the P out as this, and we can see the del P out by del D2 is equal to kappa R by kappa. So clearly it's clearly if we put D1 tends to infinity, this thing goes to this, so this would be finite. But for the broken case, so this is for the broken case, and this is a discontinuity at EPs. So first let's see the derivation of the power output. So from the equation 3 above we got this, and putting kappa 1 is equal to kappa 2 is equal to kappa, we'll get this, and this is polynomial in x1 of order 4, and we know at EP x1 is equal to plus minus g, and we can obtain the derivative which is with respect to d1 and d2. So we get the phi 1 and phi 2. We'll put these in P out, and then at EP we can put this we got this from the coupled mode theory, and then substitute, then taking partially differentiating the equation with respect to d2, this equation, and substituting x1 at EP and x1 is equal to plus minus g, we get this equation, and then finally we get this. So this has a discontinuity at EP. So let's see in the plot how where we exactly are talking about. So over here, so this is a clear discontinuity in P out with respect to, so this is d2 by d1. So let's start the plots now. So we have different regions in this plot. Let's say we start with the d minimum required for the exceptional point, which is equal to which is equal to k1 plus minus g, kappa 1 plus minus g. So kappa 1 has value 7.1 and 0.71, and this has value 0.2, which will give you 0.51. So let's say we are around over here, and we'll fix d1 and pump d2. So in this region we won't get any output. It would be, if we just plot the simple curve for the P out and D2 for fixed D1, that would be 0.51, it would be 0 initially. Then afterwards we hit this, and then we'll get a linear we will get a linear power with respect to D2, which is pretty much clear from the P out for the PT symmetric part over here. And these two parts are more interesting. Let's say we start at D is equal to 8.85 or D is equal to 0.91. For 0.85 we'll first move over here, which is PT broken part. So the plot would be, for the D1 is equal to 0.85, it would decrease initially. Intensity is inversely proportional to the pump for the PT broken part, and then we'll move to this part where we don't have any we won't have any output, so it would be 0. Let's say if it is 0, and then afterward we will go to the PT symmetric part, which will be linear. So the plot is over here, this plot. So this is the virtual EP part. This dashed line are the virtual EP. And we have a 0 against that. We won't get any power output. This would be decreasing. This is PT broken part, and this is PT symmetric part. Okay, and let's say we now start over here for D1 is equal to 0.95. We are initially in PT broken part, so it would look like initially it would decrease, and then afterwards it would like have a linear P out, which is exactly this plot, this right over here. So this is the point where we have the change between the broken part and the symmetric part, right? So like these are some points which are important to these plots. Like to 2EP, our actual solution when D1 is greater than K1 kappa 1 plus 1 SG, and to obtain the EP we can increase pump to D1 and then increase the required pump up to set the value by equation number 4 in this part. And yeah, now my colleague will start with the Maxwell Bloch equation part. Thank you.
Hello. So today I'll be explaining linearized Maxwell Bloch equations. So basically, as my friends previously explained, the coupled mode theory is very useful tool to obtain the qualitative and semi-quantitative results of our coupled resonator system, but it does not take into account many effects which affect the stability of the system, such as the spatial mode profiles, the gain saturation, the gain medium dynamics, and so on and so forth. And so we use the Maxwell Bloch equations, the semi-classical Maxwell Bloch equations, in the regime of the rotating wave approximation, which is basically means that the rapidly oscillating frequency terms in the system, they are neglected because they average out to 0 in any time period that we are looking at. So these three equations basically describe all of the electromagnetic field and all of the interaction between the electromagnetic field as well as our gain medium for the two-level system. So we also assume that we are only looking at a single polarization for these equations. So basically all the terms in this equation are E plus, which is the positive frequency component of our field. Uh, Similarly, polarization is a positive frequency component as well. Epsilon C is the permittivity loss, and sigma C is the conductivity loss. Uh, Also, omega A is the frequency at which both of the fields oscillate. Perpendicular is the spectral line width of the laser, and gamma parallel is the relaxation rate for our population inversion, which is characterized by T. So once you understood all three equations, we can start deriving uh, the differential equation that we'll use, which is basically this. So we obviously all of the assumptions and the approximations we make, they have to be invoked. So we basically uh, see that the steady state solution for these three equations, they can be obtained via the salt theory, which is the steady state ab initio laser theory, which will be exact in our rotating wave approximation for only single mode solutions, which basically means that the lasing will only occur at a single frequency, and it will approximate for well-spaced modes, well-spaced multi-modes. So, which means that basically, if you decrease the separation between each modes of frequency and go to a limit of zero, it will basically boil down to a single mode lasing solution, and then it will be more and more accurate as you decrease the spacing of the modes. So after we invoke the single mode lasing solutions, we assume those solutions, and yeah, we can pump that into these three equations, and basically we can look at the derivation now. So E plus and P plus are basically the positive frequency single mode solution. So positive frequency means that we are only considering this part and not the complex conjugate part. And if we assume a single mode solution, that means that the summation boils down to a single solution. So basically, here we see that after we substitute these two forms, we we get these three equations, and from this equation we substitute this to be T, and we simplify this to this form. After substituting this with P and substituting D from this equation to here, we get this equation, and after complex conjugating this equation on both sides, we basically simplify everything and get the form of P conjugate L. Uh, from here we can get P conjugate L, and then we substitute P conjugate L from here in this equation because it occurs in the right side of this equation. We substitute that and we get this equation. This is obviously a complicated looking equation, but after you simplify, you turn out to get this form. And after you get this form, you basically substitute what you took the previous assumption that this whole thing is considered to be T. You can basically also say that this is gamma perpendicular divided by gamma L, capital gamma L, because of this equation here. And basically, after you do all of those substitutions, you simplify and get this expression where you get a bracket term and then EL gamma L. So we again simplify this to be equal to TL. So this is equal to TL, which is the result we get here. And Then we substitute PL, which we obtain here, into the first equation, and then we get this differential equation, which is our final differential equation that we use to solve the numerical solutions of the lasing modes. And here you can see that this is a unsolvable, like this is not solvable analytically, since this is a complicated nonlinear equation, since the DL depends on 1 plus EL square kind of term, which will come in the denominator here, and also there's a double derivative here in terms of EL. So it is a complicated equation, so that's why we need to simulate this equation numerically using the salt theory, and which basically uses a finite difference method to simulate these equations. These plots will be explained further by my friend, and he will expand more on the Maxwell Bloch equations.
So, mm, the my mate has earlier got us this equation of nonlinear steady state, which has several different parameters like omega L, sigma c, omega L, tau, and dl, which has been defined here. So these are several different parameters. So now this equation would help us get the plot that we have plotted earlier using CMT. We would plot this graph by solving the differential equation numerically, and that is our sole motive of proving that Maxwell, for a single mode lasing solution, using the salt analysis method, which works very finely for single mode lasing solution. There are several parameters in this equation, which we need to choose very carefully in order to get a perfect fit for the graph, which we have choose accordingly here. Like the values have been defined here. The line width will be 0.1. Then refractive index has been, conductivity loss. All things have been defined here, and we have taken that. And to obtain a good fit, we have also taken the loss factor K equal to 0.71 and coupling coefficient to be 0.2, so that we get a good EP for this graph. Now solving now solving the now solving this Maxwell now solving this Maxwell Bloch equation, we finally get those graph. We finally find that graph for PT broken, PT symmetric, and get the threshold graph. For the parameter students, required does the required threshold graph for does the required this required threshold graph for lasing is being the function of d1 and d2. Now observing this curve for PT symmetric and PT broken, we can see that these two for PT broken, for single mode lasing, we can see that this graph have the graph plotted using the Maxwell Bloch had qualitatively perfectly matched with the results that we have obtained earlier using the CMT theory. Now, now we would be looking into this another graph, which is this one. We see that as we uh, as we fix the d2 by d1 value to around 0.566, we see that uh, which we have derived from the which we have derived from getting the parameters and using the CMT, uh, using the equation that we for exceptional point that we have obtained using the CMT. We set the d2 by d1 value to be 0.566, so that around this point the non-linear exceptional point occurs. Now as we increase the pump value, the further from the ratio of d2 by d1, as we increase the pump value, we see that the power output increases linearly. As you can see here, the straight line shows us that the power output has been increased uh, linearly. This kink in here has been also experimentally proved in the paper. Uh, Experimentally proved in the reference of the paper we had been um, solving. Now we see that from as we come from here, the output power decreases till we reach the exceptional point. Mm. Now, now when now now moving again back to our graph. Now we see here that when D1 takes smaller values than the values needed to reach EP, there is laser turn off that in observed means we see no we see no we see negative we get negative power in this region which doesn't um, which is not valid in real systems. So but we can get the virtual we can define some virtual EP for that, and we can get that virtual EP accordingly solving the Maxwell Bloch equation again, since they are mathematical equations. uh, so uh, solving this Maxwell Bloch equation for negative power correspondingly, we get our equations for the virtual EP, which are these lines. Now we move further to the now we uh, now we also see that um as we move from here, there is separation means since no since this is the region of virtual EP, no lasing has been there is a separation in the lasing, and there is a separation in lasing, and as we move in here above the threshold there is a revival is lasing. This is due to the presence of non-linear virtuality that we have observed. Specifically, power slope of laser will continue to zero intensity um, till the laser turns off, and when it turns off for higher pumps, uh, and when it turns from higher pump, we would observe power, but there would be no EP and no kink would be observed for the power flow. Now, finally, this third plot, we see the stability and instability. We talk about the stability of the exceptional point. So, from earlier, from the CMT, we have derived that uh, for PT symmetric, the delta doesn't contain any kind of imaginary part, but for PT broken, we have imaginary part in the delta. So for the thing stability of the system, we need that imaginary of part of delta to be less than equal to 0 in the PT broken phase, so that the gain balance that is lost, it would be balanced. So due to uh, so um, mm, so like satisfying our assumption of satisfying our condition for stability, um, we would we would get the proper graphs, and hence we have now proved that Maxwell Bloch equation also confirms the presence of EP.
So section 4 of this paper deals with how the same setup we've been using this whole while to demonstrate exceptional point physics can also be used as a parametric amplifier. And the way this works is that in the in this two medium setup with an air gap in between, into one of the media, say D2, say the second medium on the right, we we input a current, an infinitesimal current, which oscillates at a given frequency, say omega s. We call this the signal frequency, and and we see how the solution we had earlier inside both our media, it changes. So if the earlier solution was E L O Z e power minus I omega L t, the earlier single mode solution, which we had obtained without this additional current. We now ask that if it gets modified by del E, del P, and del D, if the population inversion gets modified by del D, the polarization by del P, and the electric field by del E, what equations will del E, del P, and del D obey? And those equations are right over here. So this is nothing but just asking for E plus del E, P plus del P, and D plus del D to together obey the Maxwell Bloch equations, knowing that E, P, and D themselves obey the Maxwell Bloch equations. And then these three equations are sort of a difference of the two. Now we might expect, looking at these equations, we might expect that we can simply ask for an addition to the solution which comes at the signal frequency. So we can ask that an additional mode gets activated at the signal frequency. But it turns out that if we just desire a solution of the form del E equal to del E S e power minus I omega st and del P equal to del P S e power minus I omega st, this does not work out properly. So we in fact need to add two additional modes, one at the signal frequency omega s and one at another frequency which we call the Adler frequency, and which is 2 omega L minus omega s. So only a solution which involves both these additional modes in del E and del P would in fact work out. So that's exactly what we demand, and so we look for a solution where del E is del E s e power minus I omega st plus del E I e power minus omega I t, and same for del P. And now if you look at the final equation, the third equation, taking such a del E and del P actually forces del D to be of a particular form, which is del ds e power minus I sigma t plus del di e power I sigma t, and where sigma is of the form omega s minus omega l. Now an important point to note over here is that del di in fact is the conjugate of del ds, but we must write del d in this expanded form even though we don't write our del e and del p in their real form. So the form of the Maxwell Bloch equations this paper is used and we have used are such that wherever they have E and P written, it's sufficient to just use the positive frequency components of E and P. But wherever the population inversion D is written, the equation expects the complete population inversion, not just one of its frequency components. That's why when we linearize the solution around the single mode solution, we must use the complete del D, which is over here. And so finally the situation is that when we add this sort of perturbing current into the second media over here, now there are three modes active inside our cavity. There's of course the initial single mode solution mode, which we know as omega L for given pumping rates, and there's also two additional modes, omega I and omega S, just as I explained above. Now, how do we solve for the spatial variation of these modes omega and omega s? So section 2 was all about solving for the spatial variation of the mode omega L, but now in this section we want to solve for omega I and omega s. So the three, if we demand a solution of this form, this form above, it turns out, and substitute this form into the linearized equations which we got over here, it turns out that del ES and del EI have to obey these two coupled differential equations, the ones over here. And so we simply have to solve these inside both media and also inside the air gap. Now a few important points to note are that these equations are different inside both the media because the parameter dl, which we see over here, is directly proportional to the pumping rate, and the pumping rates are different in the two cavities. And it's also important to note that the current is only applied in the second cavity over here, D2. So when we evolve this equation inside the first cavity, we would set this term to 0. Right. So now we and the sort of boundary conditions we must use, just as we did in the case with the single mode solution, is that we must demand that there are traveling waves to the right on the right of the right medium, and traveling waves to the left on the left of the left medium. So the solution essentially on this side must be of this form, and the solution on this side must be of this form. And this helps us because if we were to try to numerically solve the differential equation, we could just start with three with two parameters here, say the magnitude of the del E field and the del S field and the del I field over here, and this form would give us their derivatives over here, and we could simply evolve that through this cavity, through the air cap, and through this cavity, and we would know, if we start with the right parameters, if the field and the derivative we have on the left side here of this left medium matched with this form of the solution. So essentially if the derivative over here of del S of the del S field was properly related to the del S field explicitly, if it was exactly minus I omega S times the del S field, and if the derivative of the del I field was exactly minus I omega I times the del I field over here, we would know we started with the correct parameters on the right side, and that's how we could arrive at the correct parameters and hence the correct solution inside both the cavities. So let's say we do this all. What does eventually happen? So it turns out that at a given pumping rate, so say I pump cavity 1 with D1, cavity 2 with D2, and I apply this infinitesimal current. Now I can vary what signal frequency I apply this infinitesimal current at, and so for a given pumping rate D2 D1, there's a different FL or omega L, which is the single mode frequency that our cavity operates at. Now I can give my signal frequency either close to that or far away from that. Now we see that regardless of what pumping rate I choose, when I give my current at a frequency which is very close to the operating mode frequency at that pumping rate, there's a divergence in the transmission at the signal frequency. So how is the transmission at the signal frequency defined? It's probably you solve del ES. You probably solve this equation for del ES and del EI, and then the transmission at the signal frequency is defined as the magnitude, the power of signal frequency coming out of here plus the power coming out of here by mod del J square, which is the input power at that frequency. So yeah, if we define transmission this way, it turns out that whenever I give my signal frequency close to my single mode operating frequency of the cavity before giving the current, there's a divergence in the transmission. But an interesting feature related to the exceptional point is that this divergence is much larger if I'm pumping my two cavities at the ratio 0.566, which is exactly the ratio which creates an exceptional point. Which it's the smallest. It's one of the ratio. It's exactly the ratio at which you get an exceptional point. Yeah.
Started? Yeah, started. Okay. And to stop, you just open this again. See? Windows Z. Stop record. Okay. Windows G. It's recording now. You want to go now? Still recording?
Hi, I'm Jason. I will be explaining the code in this problem. So, uh, first we go on to the phase diagram where we see how this the virtual EP and EP are. Okay. So let's go down. Hi, I'm Jason, and I'll be explaining how the code works. Uh, so this is a phase diagram where which we have already encountered. Uh, this is a simple to code because we just have to code the virtual EP and the real EPs, which are straight lines, and the PT symmetric, which is another straight line. The only difficult one is the PT broken case, which is a slightly non non-linear equation given by y is equal to minus g squared by x plus k x minus k1 plus k2. The second code, we actually take the crystal and pass the wave through it. So that we start off with a wave with an amplitude of about in this case of about 0.03 to the power of half, and with its derivative being the amplitude times minus omega L into j by c, so that it's a wave going in the right direction. The So these are the differential equations being satisfied in the slabs and air respectively. And it's a little big because I had to make the double differential equation into a single differential equation, double differential into a first order differential equation. Also, since the Python solving technique I used can only solve for real numbers and not for complex, I had to separate the real part and the imaginary part. Um, so here we start off with the starting conditions where the real part is a and the derivative of the imaginary part is minus omega L by a by c, and dividing the slab into 1 million parts, we solve the equation and we get a wave like this. So given that we have taken the assumption that the electric field and its derivative doesn't change once we leave the slab, I've just taken that and put it as the inputs of the air gap, and solving that we get this, plotting it. This is what I'm plotting right now is the amplitude square of the electric field. Um, and we do the same for slab 2, where I take the ending electric field and its derivative and input it into the slab 2 initial conditions. Another million divisions later, and solving it through usual for ordinary differential techniques, we get this output. Piecing all the outputs together, we get an output like this, where the black lines indicate where the air gap was. Yeah, that's it.